sick. How do I turn the pointer on?
It's this top button, I think. There.
Oh, okay, sick. Right. Hi, everyone. I'm Zuzanna Kocjan. I'm a second-year astrophysics PhD student at the University of Maryland. And today I want to talk to you about my work on the relation between the two accretion modes and the gas dynamics in CGM and star formation. So I'm going to quickly start with some background information, but I'm sure everyone here already knows all this stuff, so I'm going to be very quick. We have two accretion modes in galaxies. We have the hot accretion mode and the cold accretion mode. The hot accretion mode is basically just a quasi-spherical gas of hot, a cloud of hot gas that is surrounding the galaxy. It is slowly falling onto the galactic disk, and while it is doing there, at a distance of around 1 virial radius, the gas gets heated up to around the virial temperature of the hot halo. And afterwards, it just slowly falls down to the disk. This mode is more dominant at low redshifts when the mass of the galactic halo is much higher. And then we have the second mode, which is the cold accretion mode. This is basically hot, dense filaments of, cold, dense filaments of gas that are like penetrating the hot galactic halo and then getting onto the galactic disk. The gas in those filaments is unlikely to shock heat. It is traveling very fast. And this mode is more dominant at low masses, so high redshifts. And so when you have this background information, we can set up this very trivial thought experiment. Namely, let's imagine that we have a parcel of gas or just some blob at a distance of around 2 virial radii away from the galactic center. So where the accretion begins in this case. And then once it reaches 1/3, it enters the CGM. And then after that, the gas gets turned into stars. So if this parcel of gas belongs to the cold accretion mode, then it's going to travel very quickly through this region. And then once it reaches the CGM, it can very quickly turn into stars because it is already cold, right? So it's cold and dense, it's basically ready. And then if that parcel instead is actually in the hot accretion mode, then it's going to be traveling very slowly through this region. And then once it reaches this area, it will actually need more time to turn into stars because it is hot. So it needs extra time to cool down and condense, right? Makes sense. So in my work, I decided, OK, I'm just going to check if that is true. Why not? For that, I used 4 Zoom simulations of galaxies. Here you can see 3 of those gorgeous halos at, I think, redshift 2. This one is merging here. The 4th one is actually the NUT simulation. The only difference between these 3 and this one is that the NUT does not have SN or AGN feedback implemented, which is important. These simulations were operated using AMR code Ramses. But I also had Monte Carlo tracer particles implemented so that I could access the Lagrangian history of the gas. And so to extract the cold gas and the hot gas, obviously I used temperature thresholds. This is the maximum temperature I found to the cold filaments can reach because of the UV heating from the background. And then this is the temperature, minimum temperature for the hot gas that I used because it's just 1/2 of the virial temperature for a Milky Way-like halo. And so, yeah, I only selected gas tracers that can turn into stars at the end of the simulation. And I also selected gas below a certain density threshold so that I can kick out gas that is transported via satellites because we're not interested in those here. OK, so moving on to results. What I found for the timescale, the traveling timescale, is that, here you can see it on y-axis, and is that for the cold accretion mode, it makes perfect sense. It's much faster than hot gas. Whereas the hot gas, well, as I said before, needs more time to travel through the halo. So yeah, the median is rounded. Makes sense. No surprises there, right? The lines grow with time because obviously the halo grows in time, so the gas needs more time to travel. However, the surprises came when I actually tried to look at the star formation timescale, so-called. So this is the time from when the particle or the gas reaches the CGM and then turns into stars. And as you can see here, surprisingly, it's actually the cold gas that needs more time than the hot gas to turn into stars, regardless of the simulation snapshot and regardless of the halo that I looked at. If you're wondering about those drops, this is caused by mergers with other galaxies. So yeah, just bumps in there. Yeah, and then when I looked at the NUT simulation, exactly the same results, except less bumps because the NUT galaxy is a bit more isolated, so there are not many measures. So yeah, we have this surprise. Now, what could be possibly causing it? So first suspect was heating. So what I did here is that I selected the cold gas that has reached the CGM, and then I have basically binned it depending on the maximum temperature that the gas reaches after crossing the CGM for the, entering it for the first time. And as you can see here, the hottest gas, so this one, is obviously requiring the largest amount of time, which makes sense. However, what is also crucial here is that even when I selected the gas that stays below the cold gas threshold, that gas is still above the hot gas, which means that the heating does contribute to the delay in star formation, but doesn't explain it fully. Now, I thought, okay, how about gas outflows, right? Recycling. Here I did the exact same thing, except with distance. And again, as you can see, particles that get kicked out to the largest distances need a lot more time to come back and form stars, which obviously makes sense because they're far away. But again, when we look at the gas that actually does stay inside the CGM, the way I define it here, it is still above the hot gas. So again, the outflows do contribute, but they don't fully explain the situation. So then I thought, okay, another approach. Let's take all the cold gas and split it into slow cold gas and fast cold gas. So in here, basically, the fast cold gas behaves as it should, meaning once it reaches CGM, it actually does form stars quicker than hot gas. And slow gas is the one that is, slower than hot gas. And what is important here is that the fast cold gas is only a tiny minority of the total cold gas that is accreted, strangely. And yeah, I don't know if you can see here on these plots, they're a bit dark, but yeah, those are the trajectories of the gas particles that I was following. You can see the filaments in here, and the hot gas a bit more isotropic. Okay, so once I had that, I looked at the angular momentum, third suspect. And here you can see the mean specific angular momentum for these three groups. And again, another surprise, actually the fast cold gas is the one that reaches the galactic center with higher angular momentum. Because we thought, okay, maybe this delay is actually caused by gas residing in rich angular momentum disk. But no, actually that is not true. It's actually the exact opposite. So again, not angular momentum. What's next? I decided to look at the geometry accretion instead. And bingo, this is basically what is happening here. Here you can see the slow cold gas being stuck in this turbulent, messy region, whereas the fast cold gas totally skips this route and then gets straight to the star-forming region. And also, so does hot gas. It doesn't get stuck and trapped in this messy region. And so it seems as if the delay is actually caused by the gas residing in that area. And so to confirm this, I also just looked at basically the components of the geometry. And so, okay, there is a lot to say about these plots, but basically the R here is just the distance between the galactic center and gas parcel. The H is just the height, and then the cylindrical radius is RC. And so what you can see immediately is that when we go up to 600 million years before star formation, is that the fast cold gas is at much larger distances away from the galactic center. And then it gets to the center very quickly. Whereas at the same time, the slow cold gas is already much closer to the disk, even closer than hot gas, but it just sits there. And it just slowly gets to the center because it is stuck in this orbiting, messy, turbulent, donut-shaped thing. And the same thing happens when you look at the median angle. This is the angle between these components. And immediately you can notice that the fast cold gas actually comes from much below or above the galactic disk, whereas the hot gas, the median is close to 0, so it must be like quite isotropic as we expect. Whereas the slow cold gas seems to be just also oscillating around the 0, like at very low angles. And you can see this when you actually look at the donut from different angles. Like this is the face-on image, this is edge-on image. Face-on, you can actually see this tiny like orbits around here, whereas edge-on, you can tell that this gas is just going like this, side to side. Yeah, and so this is what it seems to be happening. The gas is just staying there, and that is delaying star formation. So, yeah, very quick summary. Yeah, 2 accretion modes, hot and cold. The cold is traveling faster through the hot halo. The hot gas needs more time. But when it comes to star formation, the cold gas is actually delayed rather than being quicker at forming stars, since it is cold and dense already. And then, yeah, what could be causing this? Heating outflows, yes, they do contribute, not fully explain it. Angular momentum, meh. Accretion geometry, surely, yes. We can see that this region here is forming regardless of what simulation I look at and what time I look at. So, yeah, thank you.
Time for maybe 1 or 2 questions. I think
just a clarification.
Yeah.
Did you say that it's primarily turbulence that's causing your slow gas to hang around there?
It
and
is
what is the velocity difference between the slow cold and fast cold?
I don't remember exactly the velocity differences, but I do remember looking at the velocity dispersions of this region and the fast cold gas, and it seems as if this donut is just much more turbulent. And what is also interesting is that the densities of those 2 regions are actually the same. Like the density of this and of the gas here is the same, as if the donut had the same densities as the filament. So, yeah.
maybe 1 more short question. I think you, but hold on. Next speaker can come up and prepare. Yeah, go ahead.
This is really awesome. So I was trying to read it from the plots, but do you see difference in where exactly stars are formed in the galaxy, depending on if it's like hot mode or cold mode accretion? Can be like hot mode brings gas to the outskirts and it's easy to get into, and cold mode brings it to the center where there's a turbulent gas.
Yeah, so in this case, I actually specifically only selected tracers which form stars inside 1/10 of the virial radius. So I didn't look where the stars are formed depending on the accretion mode. I just selected all of them that are in the same region.
Okay, let's thank our speaker again.